Good evening. The Chemical Sciences faculty at Complutense University of Madrid has the honor to be the host for the celebration of the first workshop, Materials for Energy and Sustainability, which is an activity co-organized by the Spanish Royal Society, Madrid section, and the UCM Students Chapter. This student association is the Chemical Science faculty, was founded in 2018 and belongs to the Electrochemical Society, and it is the only student chapter in Spain by the moment. Its main goal is to promote and improve the dissemination of science and research, mainly among the junior members, and it is in this context where this workshop is integrated. It aims to present different alternatives that are being investigated to solve the current energy problem. In addition to batteries, known and used daily by all of us, other solutions include the use of thermoelectric materials, high critical temperature superconductors, or solid oxide fuel cells are different alternatives. This different system will be discussed during the 2 sessions of this meeting. This workshop has an international character because beside 2 professors of this chemistry faculty, Professor Miguel Ángel Alario and Dr. Elizabeth Castillo, there are 2 experts on this field from foreign institutions. Professor Anthony Powell from University of Reading in England, and Dr. Beatriz Molero, who was a student in this faculty, in fact, and she's currently the founder of the Canadian company CO2 Energy, focused on converting carbon dioxide into clean value-added fuels and chemicals using reversible fuel cell technology. As Vice Dean for Research and International Affairs, it's a pleasure to open this first workshop of Materials for Energy and Sustainability. Thank you very much and welcome everybody.
Okay, good afternoon. I am here as Secretary of the Madrid section of the Spanish Royal Society of Chemistry. The President of the section cannot be here today due to other previous commitments. And an inorganic chemist, it's a very special pleasure to be here today at this meeting. Our world has fundamental challenges ahead, and one of them is to make our standard of living sustainable for future generations. Science, and specifically chemistry, probably appreciation. That is why today's workshop is so important. Chemistry can provide new materials to mitigate our problems of energy availability and sustainability. I finish by congratulating the organizers of this event for bringing together such a wonderful group of speakers. This type of activities gives sense to our chemistry society.
Dear Vice Dean, Professor Maite Villalba, dear Secretary of the Spanish Royal Society of Chemistry, Madrid Section, Professor Ernesto de Jesús, thank you for being here. And welcome to everybody to this workshop, Materials for Energy and Sustainability, supported by the Spanish Royal Society of Chemistry, Madrid UCN Student Chapter from the Electrochemical Society, the Faculty of Chemistry, Complutense University of Madrid, and the Community of Madrid in the line of the 5th Regional Program of Research and Technological Innovation. I'd like to make a special mention to David Pacios and his team from Oficina de Software Libre at Complutense University for their support and for their help with all the technical part of the retransmission. David, Sara, we really appreciate your effort. In this workshop, we are going to learn about the development of new materials for energy. We know that in this moment it's crucial to search for alternative energy sources and to find new ways of using energy more efficiently. For these reasons, the topics that are going to be studied here are vital. These workshops consist of 2 sessions, and each session includes 2 plenary talks. Today, we are going to discuss the main advances in thermoelectric materials and materials for new generation batteries, while tomorrow, in the second session, we will focus on the progress in high-temperature superconductors and components for solid oxide fuel cells. Both sessions are moderated by Master and PhD students who are young members of Madrid's UCN Student Chapter and the Spanish Royal Society of Chemistry. Thank you all for your help, especially to Elena Sánchez Ahijón, who is the president of Madrid's UCN Student Chapter, Marina Tabuyo Martínez, and Marta González Barrios from the Inorganic department at UCN. It's now my great pleasure to introduce Professor Anthony Powell, our first speaker. Professor Powell graduated in chemistry from the University of Oxford, and after postdoctoral work at the same university, joined Heriot University in Edinburgh as a lecturer in inorganic chemistry, where he was subsequently promoted to reader and to professor. He was the founding director of the University Center of Advanced Energy Storage and Recovery, and in 2013, he joined the University of Reading as head of department in chemistry. Later, he held the position of director of research in chemical science. Professor Powell's research interests in solid-state materials chemistry focus on functional material with technologically useful properties. Major themes include materials for energy application, especially thermoelectric materials, novel electronic and magnetic materials, low-dimensional solids, and porous semiconductors. Many of his investigations are underpinned by neutron scattering as central facilities, for example, at ICIS Neutron and Muon Source in UK. Last but not least, he co-chairs the UK Thermoelectric Networks. So, dear Anthony, thank you for accepting our invitation and taking time out to participate in this workshop.
Thank you, Jesus, and thank you very much indeed for this invitation, and also to those people who've been working behind the scenes over the last half hour to try to resolve some of the technical problems that we've been experiencing. So what I'd like to do today is, because I think thermoelectric materials are maybe a little bit less familiar than some other categories of energy materials, I thought I'd start with a little bit of an overview of thermoelectric materials and then draw on some examples, which will be mainly from our own research. So a thermoelectric device is essentially shown down on the bottom here. this array of essentially N and P type semiconductors that are connected electrically in series and thermally in parallel. So this is a commercial device that can be picked up from RS Components or some other supplier. And essentially, if you apply a temperature gradient across that device, so from top to bottom, for instance, then what happens is both the holes and the electrons, so it's an array of N and P type semiconductors, the holes and the electrons carry heat away, and then it's rejected at a heat sink, and in doing so, it creates an electrical current within that device, that the holes and the electrons moving from one end of the semiconductor to the other create a potential difference. It can also be used in reverse, whereby you apply an electrical current to it or apply a voltage to it, and that then causes the holes and electrons to act as a heat pump, and it can act as a refrigeration. I'm going to talk principally about energy generation today. I do have a video here, but I think in the practice runs that we did earlier in the week, the video didn't really work properly, so I should probably skip that rather than risk pushing the technology to its limit. Now, talk a little bit about application areas. So as I say, if we want to generate electrical power from that thermoelectric device, then we have to put a temperature difference, a temperature gradient across the device. But it really doesn't matter where that thermal energy comes from. So it can come from industry, for instance. Steel, cement, and glass are two of the biggest areas in industry where there's a significant amount of waste heat. Transportation's another area, and certainly we've been working on materials for automotive type applications. Aerospace, these materials already used in deep space probes, for example, where there's not enough solar energy to provide electrical power, but there are also potential applications in non-safety critical areas in aircraft. And then there are the sort of more niche areas of application, which include things like wearable electronics. So we've been working, for instance, recently on a project which tries to use body heat here. There's also potential applications in terms of combining them with photovoltaic devices in order to extract some of the thermal energy that's impinging on these solar panels, for example. So in essence, I guess the message is that any source of waste heat can be turned into electricity using a thermoelectric device. Now, we'll see a lot in this talk, and if you look at the thermoelectric literature, this parameter ZT, ZT is kind of it's called a figure of merit. It's an indicator of performance. So it's a useful indicator in some respects. I sometimes think that people get a little bit too hung up on the value of ZT, but it's a useful indicator to compare across materials the level of performance. And it depends on the fundamental materials parameters, the Seebeck coefficient, the electrical conductivity, and then the thermal conductivity, which has got two components to it. It's got that due to the charge carriers, the kappa E as it's indicated here, and it's got a component due to the vibrational modes of the solid, the phonon component, which I've labeled here as KL for K lattice, kappa L, kappa lattice for the thermal conductivity due to the phonon transport. The problem in terms of designing a material that has a high value of ZT is that these parameters of the Seebeck coefficient, the electrical conductivity, and the electrical part of the thermal conductivity are all interrelated. So for instance, if we were to plot these parameters as a function of the charge carrier concentration along the x-axis, we'd find that the materials that have a very high value of the Seebeck coefficient are generally insulators or non-metallic materials with a fairly low charge carrier concentration. And of course, what that means is that they have a very low electrical conductivity. Conversely, if we go to materials which have a high electrical conductivity with a high charge carrier concentration, they've got a low Seebeck coefficient. So there's a trade-off in terms of the numerator of this expression. So this S squared sigma term is known as the power factor, and that sort of peaks somewhere in the middle here, which corresponds to heavily doped semiconductors. There's also as I say, the thermal conductivity element of that, which is an issue, is that whilst the lattice part of the thermal conductivity is largely independent of the carrier concentration, the electronic part will of course get higher the higher the electrical conductivity, and in fact they are directly related to each other through something called the Wiedemann-Franz law. So to try to encapsulate the problem, it's a multi-parameter problem really, but to try to encapsulate it in one statement, I would say that one of the problems with the thermoelectric is that we need something that gives us the conduction of electricity that's like a metal and the conduction of heat like an insulator, so in the same material, and that's a major challenge. The only current commercial material is this one, which is bismuth telluride. This is a layered structure, so it's these blocks of octahedra that, so this is like the metal dichalcogenide structure, but taking pairs of them which share common faces. So we have these paired blocks and then a van der Waals gap and then another block of bismuth telluride. So it's a layered structure. That in itself can introduce some problems because it means that the properties are generally very anisotropic. And often in terms of powder consolidation, where we're pressing an ingot, we need to be able to cut that ingot in particular ways in order to measure the transport properties, both parallel and perpendicular to the pressing direction, because the anisotropic structure gives us an anisotropy in terms of properties. The nice thing about bismuth telluride is that it's possible to make chemically compatible N and P-type variants. So if you remember, the thermoelectric device has both N and P-type semiconductors. So we could make both N and P-type versions of it through suitable doping. It depends a little bit on how it's fabricated and manufactured, but typically the ZT of bismuth telluride is between about 1 and 1.3 at 400 Kelvin. So that sort of sets a benchmark at these kinds of temperatures in terms of performance. And that's why, as I say, bismuth telluride is really the only commercially available material currently. And the reason that this ZT is important is it feeds directly into the efficiency. So this is showing the efficiency here on the y-axis as a function of the hot side temperature on the x-axis as a function, or for, I should say, different values of Z. So these are Z now as opposed to ZT. Bismuth telluride with a ZT of about 1.3 at 400 Kelvin. That puts it between this, somewhere between this 002 and 003 line, but of course we're down at 400 Kelvin. So it means that typically we're talking of an efficiency of only 2 or 3% in most applications. Perhaps more serious from the point of view of usage across a wide spectrum of temperature is that the performance falls off quite significantly at higher temperatures. And for that reason, we really, I would say, we need a portfolio of materials that cover the applications in the different temperature regions. So we've got down at the one end here, we've got things like sensors for medical devices that maybe run off body heat, all the way through things like automotive and the aerospace, which are at the higher end of the temperature range. And if we look at the performance of materials, so this figure on the top left here is actually a chart that my good friend and colleague Bob Freer at Manchester has produced for a forthcoming compilation of data. And it's not important really what each of these compounds is. The main point I wanted to try to illustrate from this figure is that different materials show their maximum values of ZT at different temperatures. So for instance, 1A here is the bismuth telluride, and you can see as we go to higher temperatures, it falls off quite sharply in performance. Its peak performance is around about 400 Kelvin. Whereas something like lead telluride, which is this one, for instance, shows its higher performance at much higher temperatures into this sort of high T region. And similarly, we have other materials, for instance, boron carbide here, which is the one in black, number 12, that keeps on going up and will just keep on going up for quite some way beyond 1200 Kelvin. So it's a high temperature material. So we really need to be able to design materials towards the temperature appropriate to specific applications. A further constraint that we have is really on the actual component elements themselves. So most high performance thermoelectrics to date, including bismuth telluride, have a appreciable quantities of tellurium in them. So bismuth telluride down at ambient type temperatures, lead telluride at higher temperatures. The abundance of tellurium in the Earth's crust is about 1 part per billion, which is about the same as gold, for instance. So what we really want to be doing, this is the periodic table shown here on a logarithmic scale where the height of each of these tower blocks is proportional to the abundance of that element in the Earth's crust. And you can see tellurium is really down on the floor there, whereas really we'd like to be using some of these much more abundant elements, maybe sulfur, silicon, the transition metals, in order to get something where we can make large amounts of material that perform well at the temperature appropriate to a given application. So how do we overcome that fundamental problem of having three intrinsic properties of a material that contribute to ZT, but they're interdependent on each other? Well, there are a number of design strategies that as people have studied more and more thermoelectric materials, they come up with a range of design strategies. I'll speak about some of these in today's presentation. So for instance, the phonon glass electron crystal has been quite a popular way of achieving high performance, because what it does is introduces cations into cavities which are really too large for that cation, and as a result that cation shows localized vibrational modes. It's termed a rattler. They're often referred to as rattling modes, and those rattling modes can interfere with the phonon propagation, so it's affecting that kappa L component of the thermal conductivity without necessarily impeding the electrical transport, which happens through some kind of framework. This is a scudridite, which we'll be seeing later. Another way of influencing that thermal conductivity is essentially by creating interfaces, and that can be done by introducing what are called nano-inclusions into some matrix. So there's a series of materials Mercury Canetsidis developed called the last phases. They've got nano-inclusions within what is essentially a lead telluride matrix, or indeed introducing a second phase into that matrix, and then we get phonon scattering at the interfaces between the two phases. It's also possible to do some microstructural engineering. This is something I won't be speaking about today, but you can do grain boundary engineering to effectively scatter phonons selectively compared to scattering electrons. Phonons typically have a longer mean free path than electrons do, so therefore you can actually design your grain boundaries to impede the propagation of phonons without necessarily affecting the electron transport. Resonance states is again one I won't speak about. This is really trying to tune and adjust the band structure itself by introducing fairly deep-lying impurity states to introduce a perturbation into the band structure. So for instance, thallium in lead telluride has a prime example where resonance states give rise to a high thermal conductivity, a high thermoelectric performance. A type of material that I will speak about quite a lot, because we've been doing a fair amount of work on this over the last few years, is what's called a phonon liquid electron crystal. And this is a material where we have some sort of lattice, underlying lattice with mobile cations usually within that lattice. And at some critical temperature, those cations, effectively that sublattice, either melts or partially melts, and that then could lead to significant reductions in thermal conductivity. And finally, something that was first proposed by Hickson Dresselhaus, Millie Dresselhaus, probably over 20 years ago now, is that if you decrease the dimensionality of a solid, then you actually introduce more discontinuities into the density of states. And given that the Seebeck coefficient is proportional to the derivative of the density of states at the Fermi level, if you can introduce discontinuities and then fill up to that point with electrons, then it's possible to get enhancements in Seebeck. I think to a certain extent the jury is still out on that one, because I think there are also, when you go to low dimensional systems, you also introduce some interfaces between layers and so on, and that can also affect the thermal conductivity. So this is some work that we've done very recently. So we've not yet even published it on nanocomposites of bismuth telluride. So this is trying to take the kind of current state-of-the-art material at low temperatures and try to improve it. So what we've done is we've done a colloidal processing route where we essentially mix the bismuth telluride with known amounts of graphene oxide, And after some treatment, we do some decomposition of that graphene oxide to reduce graphene oxide. So we introduce essentially a carbonaceous phase that's well distributed throughout our bismuth telluride. And we can follow that process using Raman spectroscopy. So this curve right at the very top here, for instance, is a 1% reduced graphene oxide bismuth telluride composite. And the important thing to note really is that this carbon, what's called the 2D peak, which is present in graphite, is not present in the composite. And also this carbon G peak, which is very sharp in graphite, is broadened considerably. And also you'll notice the intensity ratios of these two peaks have swapped around. So all of those factors together suggest that we don't actually have graphite there. We don't really have graphene there either, as far as we can tell, but we probably have few layer graphite-like sheets. So it's somewhere between bulk graphite and single layer graphene. And what that achieved is it allows us to have significant reductions in the thermal conductivity. So I mentioned the anisotropy of bismuth telluride. So these are measurements made parallel to the pressing direction and perpendicular to the pressing direction. But you can see that in both cases, as we add some reduced graphene oxide into our material, we get quite significant reductions in thermal conductivity in both cases, and in fact, up to about 30% of reduction. We find that the optimum contents around about, for the thermal conductivity at least, depending on which direction we're measuring, either 0.25 or 0.58%. And what that does is it increases our figure of merit. So although we get a slight degradation of the electrical properties when we make the composite, that's offset by those quite substantial decreases in thermal conductivity. And we end up increasing ZT by about 20%. So at our sort of maximum ZTs here, this is the perpendicular orientation, we can get up to about 1.6, for instance. What's also interesting, though, is that we can actually improve the performance even of the pristine phase that doesn't include the carbon. And we think that that's because essentially by putting it through this colloidal process and the ultrasound, we actually reduce the grain size quite significantly, and that can contribute to reduced thermal conductivity and consequently higher thermoelectric performance. Now, I mentioned as an alternative to compositing that there's a class of materials called phonon glass electron crystal materials. So this is some work that our chairman this afternoon actually carried out whilst he was at Reading. This is some filled skutterudite. So here's the skutterudite structure. It's essentially the ReO3 type structure, and in its normal form, something like cobalt antimonide, quite a high thermal conductivity. It has no cations in these cavities. It's just that octahedral-based framework. If we introduce some rare earth cations into that cavity space, we have to adjust the electron count of the host as well. So we have to replace quite a lot of the cobalt with iron in order to maintain the appropriate electron count, because this is, of course, donating 3 electrons when it goes into that cavity. We can reduce that thermal conductivity by about a factor of 8 or so. And that can give rise to quite significant performance enhancements. So what our interest was really was thinking about, well, if a single rare earth cation with the localized vibrational modes can cause significant reductions in thermal conductivity, what happens if we were to use multiple fillers? Because as we can see here, different fillers have different vibrational or resonance frequencies, and therefore they're going to interfere with different parts of the phonon spectrum. So that was our motivation, and also because we were working on a project that was related to energy recovery and exhaust systems, we wanted to be able to scale up. So we started looking at mechanochemical alloying to make these materials. So that allows us to make batches significantly larger than traditional sealed tube synthesis. It also, as we can see for the electron microscopy here, it gives us, here are mechanically alloyed materials, here are materials synthesized conventionally by high temperature methods. It gives us both a smaller grain size and a narrower grain size distribution. So the grain size is quite significantly smaller than it is in the material from high temperature synthesis. So in terms of the single versus the double filling, what we can see here is that on these plots is the thermal conductivity, which is the key thing that we're really targeting. we can see that the triangles are the conventional materials, and the circles are the triangles are the single-filled materials, the circle are the double-filled materials, and then for each we've got both the conventional and the ball milling. So the first thing to notice is actually the preparation by ball milling it gives us a slightly improved, or in other words, lower thermal conductivity, and also that the double filling is giving us a lower thermal conductivity than if we had single filling. So that was what we set out to achieve, and that's then reflected in the ZT values here, because we can see, unfortunately, we've now changed our symbols. So now the double filled are the triangles, and we can see that the performance of the triangles, whether made by conventional processes or by ball milling, is significantly improved over that of the single filled materials, and we get a maximum ZT of about 0.93 at 823 Kelvin. So that seemed to sort of vindicate the strategy of saying, well, what happens if we use more than one filler, and we aim to introduce ions, rattlers with different vibrational frequencies? It does indeed give improved performance. So we then started thinking about module construction. So we'd previously collaborated with Gao Min at the University of Cardiff on single-filled scuderidites, where the N and P type were both single-filled. So this is one of the modules that they produced from our materials. This is a 9-couple array. And what's referred to in this diagram as the Cardiff module, you can see actually gives about 3.5 watts per cubic centimeter. So in other words, if we compare that with the one in pink here, which is a commercial bismuth telluride module, you can see that what we're really getting is we're getting bismuth telluride performance, but now at somewhat higher temperatures. And we get a maximum power output of about 0.16 watts from this module at 365 degrees C. So having made the doubly filled materials, of course, we then wanted to see what they performed as in a module. So here, where the N and the P type are both doubly filled, and we can see that the output power now is in watts. So it's not directly comparable with what's on the figure on the bottom there. But if I put the data from the bottom and I put it onto the same scale, the maximum performance that we have in the singly filled scuderidites is where that star is. So what we can see is we've significantly improved from round about 0.2 here watts. We've improved that so up to something around the same temperature, at least around the 1 watt. And if we go to slightly higher temperatures, we managed to get a maximum power out of this of 1.8 watts. So again, that improved performance in the materials feeds through into an improved performance in the module itself. And we end up with something that gives us, at the highest temperatures, our maximum efficiency comes out as about 4.5% efficiency. So we went on from that and started thinking about, well, if we're going to use these, we need to be able to scale them. And this is where the ball milling became important, because we started preparing batches in 60-gram batches. That allowed us, or I say us, allowed our collaborators at University of Cardiff to produce batches of modules, 12 modules out of a 60-gram batch of N and a 60-gram P type material. They also developed a high throughput screening technique to check these modules rapidly, because module construction is a major technological challenge in its own right. And they found that actually across the batch of 12 modules, the internal resistance was about 101 milliohms, but only varied by plus or minus 1 across the batches. Now, despite the fact we get materials with high ZTs, so here are the materials that went into these high volume power density modules, we're at ZTs of about 1.1 to 1.2 maximum. The module ZT at 300 Kelvin, so down here, is only about 0.12, whereas the materials themselves are maybe about 0.2, just above. So we lose a lot of performance in fabricating the module due to contact issues and so on. But nonetheless, we do get something that's about 4% efficient at a delta T of 362 Kelvin. And that then gives us something. It produces about 17 watts per cubic centimeter. And these were then tested. For instance, this is a Ford 2-liter engine. These modules were tested on that engine in terms of the extracting the waste heat and converting it into electricity. And this generates about 500 watts, about between 400 and 500 watts. So we can actually start to use materials in real applications. In terms of the rest of the talk, I'm really going to focus on sulfides. And what I'd like to do is just very briefly say why sulfides have attractive features. Many of them, including TiS2 that's shown here, are low dimensional, so that gives them a very highly structured density of states. The metal-sulfur interaction is quite covalent, so that means that we're going to get broader bands and higher carrier mobilities. It's also very polarizable as an anion matrix, so that means that we're going to see significant cation mobility and potential for non-liquid electron crystal behavior. Sulfur is also incredibly abundant, so that point I made earlier about the abundance of the materials becomes really quite important. And we were really struck by the fact that if you take TiS2, these are some data from the literature, you find that electrically TiS2 is actually quite good. It's performing in quite a comparable way to bismuth telluride. What kills it is the thermal conductivity. So at 300 K, ZT drops from about 0.86 down by about a factor of almost 5, and that's predominantly because of the thermal conductivity. And the other point really that attracts us about sulfides is that because of the sort of temperature range in which they're stable and they show high performance and so on, they're well suited to industrial waste heat. And some estimates of industrial waste heat indicate that about 80% of it is actually released in this temperature range over about 373 to 535 Kelvin. That's just a very good range for sulfides because sulfides are not especially stable at higher temperatures. So our first foray really into sulfide thermoelectrics was what are called shandite, based on the shandite mineral. It's a half metal. It's unusual that it has a very large Seebeck for such a low resistivity. So at 350 Kelvin, its Seebeck approaches minus 60 microvolts per Kelvin, and yet the resistivity is still less than 0.3 milliohm centimeters. So it's quite an unusual combination. It also has the attractive feature that although not low dimensional, it's pseudo low dimensional. So we have these Kagome-like layers here, these Kagome network type layers of cobalt and tin. The blue are the cobalt, so every CO3 triangle is then capped either above or below with a sulfur atom like that. Then the layers are joined together with a second tin atom, which is in a trigonal antiprismatic site. So we get this sort of pillared layer structure. So although not a true layered structure, it has low dimensional character. And what that means is we have a highly structured density of states, as we can see here. These are some band structure calculations from the literature. Our collaborators at Reading have also done some spin and polarized calculations, which confirm that it is a half metal. But the important point is in the region of the Fermi level, what we have is we have two bands, the upper of which is partially filled in the stoichiometric end member. So what we've been looking at is can we lower that Fermi level through this region here of a highly structured density of states and increase the Seebeck coefficient and improve the thermoelectric properties. And in fact, we can go, if we use something like indium, for instance, which each time we put an indium in, it removes an electron, we can go from a 47 electron material to a 45 electron material. And at the midpoint where we have a 50-50 tin-indium mixture, it's a semiconductor because the upper band is empty, the lower band is filled. And then if we go further, we start depopulating this lower band again. So rather than showing all of the properties, I thought I'd just summarize really what's happening as we replace tin with indium here. What we find is that our Seebeck starts to increase as we move towards a more semiconducting region where the upper band is empty and the lower band is filled. Our resistivity also increases. And in fact, when we get to that 50-50 mixture of tin and indium, we do see at that point and just beyond, we do see semiconducting behavior, and then we come back out the other side and it becomes metallic. So this is quite an unusual example of a metal to semiconductor to metal double transition. as a result of chemical compositional changes. When we get to that second metallic region, the Seebeck coefficient never really recovers. It doesn't get the values that we get before that halfway point. And as a result, the power factors beyond that 50-50 composition tend to be quite miserable compared to those before that 50-50. And we can see that graphically here at 2 temperatures. It sort of falls off a cliff edge as we get to that 50-50 composition. Our thermal conductivity doesn't really change very much in terms of the lattice contribution, and that's not surprising because the mass of tin and indium are almost the same. They're right next to each other in a periodic table. But we do get a broad minimum in the thermal conductivity as we approach that 50-50 mixture. The 50-50 is at the lowest point here. We get a broad minimum due to the fact that we get the electronic contribution shows a minimum at that point because, of course, that's where the resistivity is highest. So the net result of that is we get quite promising figures of merit before we get to that 50-50 composition. We're reaching 0.3 at our maximum point here, and that's at about 675 Kelvin. But as we get closer to that 50-50 composition, they start to decrease, and then it falls off a cliff edge, and we get very low figures of merit in that second metallic region. So another way that we can tune those properties of adding and removing electrons is actually to focus on the A site cation, so that's the cobalt cation, and replace it with either iron, which removes some electrons, or nickel, which will add them. If we use nickel, we find that actually all that happens is that we add more and more electrons to that upper band, and the material becomes increasingly metallic, and the thermoelectric properties really fall off quite dramatically. Whereas if we do iron, we see a fairly limited range of solid solutions, so only up to about 0.6 ions, and we degrade the electrical properties, which is the resistivity and the Seebeck coefficient. So we see this resistivity rises, the Seebeck rises as well, coming down. It becomes more negative in this sense. But the important part is that the increase in the value of the Seebeck outweighs the increase in the resistivity, and consequently we find that we increase our power factor. And therefore, what we find is we actually get ZTs, which are slightly improved, maybe not quite as much as they are when we tinker with the B site cation, the tin cation, but nonetheless, we can achieve a similar result by adjusting the electron count through the transition metal cations. And then, of course, we can combine those two features. We can do substitution of both the transition metal and at the main group cation site. What we find when we do that is that we seem to enhance the two-dimensional character of the material, because what we see is we see quite a significant increase in the C lattice parameter, for example, and we can push our ZT, our maximum ZT, up to about 0.28, but at a relatively low temperature. This is only 473 Kelvin, so that's quite a good value of the figure of merit at that temperature. Now, we've done quite a lot of combinations of cobalt, iron, tin, indium, but what we find is that the highest ZTs are always at a similar total hole content. So that is when the iron content, which is given by X, and the indium content given by Y add up to 0.9 or thereabouts. So here are 3 different compositions with 3 different values of the iron content and the indium content, and you can see the properties are all quite similar. So there's something about that 0.9 hole content that is important. And from our band structure calculations, we find that what we're doing really when we go towards 0.9 is we're moving that Fermi level more and more into a highly structured density of states. So that was really our first foray into sulfide minerals. And since then, we've looked at a range of sulfide minerals. I won't be talking about all of these today. I won't be really talking about tetrahedrite at all, but I'll say something about bornite and also the zinc blende related materials, which are derived from the corner link tetrahedra that are in zinc blende, chalcopyrite and the kestrite stannite pairs in particular. Chalcopyrite is a really quite interesting thermoelectric material because it's a rare example of an N-type material, and it has quite promising electrical transport properties, but very poor thermal conductivity. So its thermal conductivity is similar to an unfilled scutteridite, about 9 watts per meter per Kelvin, And consequently, its figure of merit is only about 20 to 30% that of the best P-type sulfides. So what we've been doing in a very recent project, and this is going on at the moment, in fact, some of this work was presented at the VCT conference this morning, for example. We're trying to optimize the carrier concentrations through substitution either at the copper site or at the iron site in chalcopyrite, and combining that with grain size reduction using high energy ball milling, and also trying to use the microstructure to control the thermal conductivity. So I'll just choose one example from this system, which is the copper chromium system, where we've substituted copper with chromium. And what we find is that if we do that, we improve the resistivity. So the resistivity falls quite dramatically. And also, surprisingly, we actually we don't impede the Seebeck coefficient as much as we might have expected for this reduction in resistivity. So although the Seebeck coefficient does indeed get smaller in absolute terms, it's not as much a reduction as we might have expected. And therefore, we almost double our power factor compared to the end member phase. However, the fly in the ointment is that we find if we take the Seebeck and resistivity at a given temperature, and we're choosing 673 here, we see that they vary in a non-systematic way with chromium content. We might have expected them to vary steadily as we increase the amount of chromium, but instead of that, they follow this sort of double zigzag type curve, and that mirrors the carrier concentration, or the changes in carrier concentration. So that really led us with our colleagues at Manchester as part of the project to look at the electron microscopy. And what we find is we find inclusions within these materials. This is just one composition here. This is 4% chromium. We find inclusions over quite a wide range of length scales, from the sub-micron level up to quite large inclusions like this one, which are almost 100 microns. And we found that actually the EDAX, or the energy dispersive X-ray data from the microscope, actually tells us that whilst the major phase is consistent with a chromium-doped chalcopyrite, these inclusions, this secondary phase, for instance, is a chromium-rich secondary phase, and we think that is what is affecting the carrier concentration in a non-systematic way, because it will depend on things like thermal history in terms of the formation of those inclusions. And we think that that is actually what's causing that apparently random variation in properties of the electrical transport properties. However, these inclusions seem to have a very beneficial effect on thermal transport because they act as phonon scattering centers, and they reduce the lattice contribution of the thermal conductivity. So that's this curve, set of curves here. This is the lattice contribution, this is the electronic contribution, this is the total thermal conductivity, reduces the lattice contribution to thermal conductivity by about 35% at 673 Kelvin. And that actually allows us to increase our figure of merit by a factor of almost 3 compared to the end member copper iron sulfide. And we can get up to, at the moment, 0.31 at 673 Kelvin. So moving on from chalcopyrite, if we introduce not just 2 cations into the zinc blende structure, but we introduce 3, there are 2 principal possibilities, the kestrite and the stannite structure, which differ only in the way that the ions are ordered. So for instance, if this was an A site with copper in it, and the orange ones here are copper, in the kestrite structure, the copper in every metal layer. In the stannite structure, they're restricted to 2 out of the 4 layers. These are very difficult to distinguish by X-ray diffraction, and there's a lot of confusion in the literature, and we've written a whole paper on identifying which are the stable phases for different compositions. I won't go into that lengthy story now, but just to say that a combination of neutron diffraction and DFT shows that it's the kestrite structure. When A is copper, is partially ordered, and when A is silver, it's fully ordered. And the main reason for our interest in these, as I said, the chalcopyrite itself has got a thermal conductivity of about 9 watts per meter per Kelvin. That of the kestrite stannite type materials is about 1/3 of that at 3 watts per meter per Kelvin. Now, kestrite end member itself has a slightly odd property, which I'll come back to, hopefully, if I've got time towards the end, in terms of a phonoliquid electron crystal. It appears to show in this region here what has been referred to as a semiconductor to metal transition on heating. So here's the resistivity, clearly semiconducting behavior, and then it turns around and starts to increase, and the Seebeck show anomalies as well. And also we find that DSC data show quite significant changes in slope in that region, which maybe show up more clearly if we take the derivative of the heat flow. But nonetheless, we have something going on in that region where we have quite marked changes in electrical properties. Now, as I say, this has been described as a semiconductor to metal transition. I think it's unlikely to be a true metal because this is quite a high Seebeck coefficient of about 230 microvolts per Kelvin. And it's also quite a high resistivity of about maybe 15 milliohm centimeters to be a conventional metal. So our belief is that it's actually a transition from an activated semiconductor to a degenerate semiconductor. But to study this, we took this, Jesús mentioned about the ICIS neutron facility. We took this to the Polaris, which is an instrument within this aircraft hangar type facility here, which is one of the Target Station 1 instruments. Polaris is a multi-bank instrument. So this is just one bank from Polaris as a function of temperature. And as you can see, surprisingly, there's very little variation in the neutron diffraction patterns as we heat this up. And if we actually do the Rietveld refinement, we find that when we get through this region, this gray stripe showing the region where those electronic anomalies are, we see no lattice parameter anomaly either. Now, fortunately, the student, PhD student who was doing this, whilst initially disappointed, decided to look at this in a bit more detail. And what he found is actually, if we look at the site occupancy factors, initially we have this disorder between the copper and the zinc sites. So it's not a 50-50. It's a slight preference for the copper in one site, in the 2C site, than the other site, the 2D site. And then there's a copper that fully occupies this 2A site. So this is our room temperature structure. But when we heat it up, it appears to get to an order-disorder transition where these copper and zinc cations become fully disordered. So that would be this dotted line here. This would be 0.5 site occupancy factors in each. But at the same time, the actual total occupancy of that site falls away. And also, the occupancy of this site that was fully occupied by copper starts to fall off. So what we find is that the copper-zinc disorder is accompanied by a delocalization of a fraction of the copper ions. And in fact, by the time we get up to our highest temperature of 973 Kelvin, we find that the crystallographic formula it involves about a 30% deficiency of copper within that formula. And when we do a difference Fourier map, we see that that copper is actually distributed over a whole range of interstitial sites in this structure. So it looks as if that copper sublattice is starting to melt. So it looks like phonon-liquid electron crystal type behavior. And that's associated then with this change from an activated semiconductor to a degenerate semiconductor. So I realize I'm probably getting close to the end of time, so I'll go through some of the remaining material in a reasonable speed. We've done some hole doping on that end member phase. We get a single phase region up to about X of 0.15. So in other words, what we're doing is replacing germanium-4 with some copper. That requires the copper to be oxidized from copper plus to copper 2 plus, and consequently we introduce some holes into our structure. What we see then as we increase that hole concentration, the resistivity falls. And also, of course, then there's a corresponding fall in the Seebeck. And although the phase transition is still evident, you can see that it's gradually being suppressed. And we think that that's because there have been some calculations that suggest that the copper defect formation energy is increased as we make copper-rich phases. So it becomes more difficult for those copper ions to delocalize and for that copper sublattice to melt partially. So we get thermoelectric properties. We get up to, I won't go through these in detail, but again, the power factors are increased as a result of those changes in the transport properties. The thermal conductivity is also increased, principally because of the changes in the electrical contribution, which are shown here. But nonetheless, this increase in the power factor is sufficient to increase the ZT slightly, and we get up just about to about 0.2 at 600 Kelvin. So then we thought, well, what happens if we replace that zinc with a magnetic ion? Because there's been some studies which suggest that if you have a magnetic ion there, the effective mass of the carriers due to coupling between the electron and the magnetic moment, those effective masses increase, and that can actually be beneficial for the Seebeck coefficient. So we took this end member phase and we essentially tried to do the same process with it, replace the germanium-4 with some copper, which causes the copper to oxidize to copper-2 and introduce more holes and hopefully improve the transport properties. There's one slight fly in the ointment with this phase, and we still don't fully understand this yet. If we do the measurements of the resistivity and the Seebeck on cycling, we find that actually the resistivity gradually falls from the first to the second to the third cycle. After the third cycle, it's more or less a constant value, and we see corresponding changes in the Seebeck as well. We're not quite sure why that is yet, because any thermal analysis that we've done suggests that the changes occur at significantly higher temperatures than we're getting to here. But nonetheless, once we've done that doping, the materials become stable with respect to cycling, and they have a significantly lower resistivity. You'll notice there's an axis break here. And although the Seebeck coefficient is reduced, there's a 3 to 5-fold reduction in the resistivity on substitution. And that means that, again, that's sufficient to improve our power factors. We also get a slight increase in thermal conductivity, but not as big a change as the improvement in the power factors. So the net result is that we now get up to a figure of merit that's about 2.5 times that of the unsubstituted phase, and significantly, in view of the fact we were trying to get an improvement as a result of a magnetic ion being here, about 50% higher than that of the zinc analog. So we're up at about 0.3, but I would stress at quite low temperatures, at 200 degrees centigrade. So it's quite useful for industrial waste heat type application. So to finish, I just have a few slides on sort of that phono-liquid electron crystal type behavior. And the archetypal example in many ways are the copper sulfide and copper selenide of this type, which at high temperatures are anti-fluorite type structures. And it's found that the copper ion mobility at high temperatures leads to a melting of the copper sublattice. So effectively, the anion lattice stays the same. The copper sublattice melts, and it assumes a liquid-like state. And that impacts substantially on the thermal conductivity and reduces the thermal conductivity quite markedly. And ZT maximum reaches about 1.6. However, ironically, it's that ion migration that leads to these materials degrading in use, because if they're subjected to a temperature gradient and have liquid mobile copper ions, and there's also a potential difference being generated, you'll get copper ion migration, and it's seen that copper starts to plate out on one face of the thermal elements under a sustained operation. And of course, then the performance degrades. So what we wanted to do is we wanted to try to stop that migration. So we looked at this material bornite, which is a high temperature phase, is also anti-fluorite related. The difference now, this would be the end member here without any copper deficiency would be M8S4. This is M6S4. So that means there are 2 vacancies per formula unit, and those are distributed at a high temperature. The vacancies, the copper and the ions are distributed randomly over tetrahedral sites in the anti-fluorite type structure at high temperatures. It has a low thermal conductivity, and in principle, we think that the ion cations are going to suppress that copper ion migration, but unfortunately, the electronic properties are low, and we get a ZT of only 0.4. So we're going to look at chemical substitution to increase the power factor without impacting on that low thermal conductivity. So I'm going to go through this fairly quickly. We've done 2 different things here. We've used copper deficiency, so we've made some copper vacancies. So again, a similar strategy that has to oxidize some of the remaining copper to maintain charge balance. It introduces some additional holes. We do get some significant improvement in the electrical properties. The power factor is more than doubled. The thermal conductivity is also slightly reduced, but the main impact is on the electrical properties, which is what we were targeting. And we can get a ZT that exceeds 0.6 in that material. We can get similar performance on a similar basis by just tuning that copper to iron ratio, which again results in oxidation of some of the copper. And once again, we can get to ZT of about 0.6. So the final example I'll show is where we sort of combined two strategies, is that we wanted to adjust the copper to iron ratio whilst also having some vacancies present. So this is no longer copper 5, this is copper 4.94. So we introduce some vacancies, we then adjust the copper to iron ratio. So once again, we see significant improvements in the electrical resistivity, which falls, which then feeds into quite large increases in power factors. Power factors are more than doubled here. And then we look at the thermal conductivity. We find that it does increase, but we're not impacting on the thermal conductivity quite as much as we were in those other series. And I think that's probably because of the vacancies. And we reach a ZT maximum that's almost 0.8, 0.79 at a very low temperature of 550 Kelvin. So this is actually one of the best performing materials in this industrial waste heat region. Interestingly, the electrical properties and the Seebeck coefficients, regardless of which series we take, so these are the three different series I've just mentioned, they seem to follow a common curve. And in fact, the power factor seems to scale almost linearly with the copper 2 content. So as I say, each time we're doing these changes, we're trying to modify the copper 2 content to introduce some more holes. We see that we increase the power factor in an almost linear fashion with the copper 2 content. However, to get the maximum performance, this is where we get the highest ZTs here, it's important that we don't just have the optimized copper 2 content, which is about 2 to 3%, but we also need those additional vacancies. And then finally, that reproducibility issue, we seem to have cured that as well, because if we do 8 runs here, we find that there's virtually no change from one run to the next. So it appears that the strategy of introducing some iron into the anti-fluorite structure has actually succeeded in terms of avoiding some of that degradation. So this just shows where some of those materials sit. I'm not going to spend a lot of time on this. I'd like to get to the summary slide in a moment. But just to show that at 550 Kelvin, bornite is probably the best material around at the moment, even better than the P-type tetrahedrites, which have been much more studied. But you'll notice that down here, we're really struggling to get comparable performance out of N-type materials, the ones that have that green box there. So in summary, I hope I've shown that there's a range of alternatives to bismuth telluride, which contain earth-abundant elements. We do have a number of materials design strategies, some of which I've discussed today. But there are challenges. Achieving comparable performance in both N and P-type materials is an issue for materials such as sulfides. So here's a graph, for instance, of a review I wrote fairly recently. All of the solid points here are P-type materials. The open points, which are down here, are N-type materials. So there's a long way to go to get compatible N-type materials with similar performance to the P-type. Material stability is also an issue, and that applies to any of these materials I've mentioned. Scuderidites, for instance, show volatilization. Sulfur can volatilize from sulfides either during processing or operation. Ion migration, as we've seen with the phonoliquid electron crystals, can also impose limits on how these materials are used. And then the whole issue of device performance, and this is not something we've done ourselves, this is something we've done in collaboration with the University of Cardiff. Device performance is a whole new issue on its own, and I think it's a whole series of research projects once the material's been developed. So finally, just to acknowledge, I won't go through them one by one, but the people at the University of Reading who've done this work, a combination of postdocs and some PhD students who are now completed, people like Sebastian Long, and the people who funded this work, and then our collaborators at other institutions. And I'll just leave you with a very quick advert for anyone whose interest has been sparked in thermoelectrics. There will be an RSC volume coming out towards the end of this year in their inorganic materials series on inorganic thermoelectric materials. And finally, I'd just like to thank you for your attention.
So thank you so much, Professor Powell, for such a nice talk. I can see that so far there's no questions, so I hope that the people attending can make questions. But in the meantime, I'd like to ask myself.
Mm-hmm.
So, because you said that when creating a thermoelectric module, there are some electrical loss because of the contacts of the materials, of the pieces in the module. How could this be solved or improved?
You have to be very careful. It's quite an involved, a complicated device. It looks quite simple because it's just a block with N and P type materials. But on those N and P type materials, there are diffusion barrier layers to stop ions migrating. There are electrical contacts. There are solders. There's then a ceramic layer. It all has to be joined together, and the key thing seems to be those electrical contacts, and it's about finding the right solder that forms a mechanically stable bond to the surface of the thermoelement, whilst also maintaining a good electrical contact. And where we've struggled with the scuderidites is actually finding a solder that actually operates at the high temperatures where we'd want to use a module. So although we've got quite good performance, the performance, if we went up another 200 degrees, would probably be even better. But unfortunately, our solder melts by the time we get to that point. And it's a question of finding the right solder in order to get both good mechanical contact and good electrical contact.
Thank you. I have one more question. How easy is it to prepare composites of bismuth telluride and graphene oxide? Do you manage to obtain a homogeneous mixture?
Yes, we do. I didn't show it on the interest of time, but as well as those individual Raman spectra that I showed, we've also done Raman mapping of the surface of the composite. So we make the composite, we press a pellet, we then map the surface with Raman spectroscopy, which shows up the different carbonaceous regions. And those regions are actually very evenly distributed. I think it's because we're going down to that colloidal level when we do the mixing that we can get good homogeneous mixing there.
Okay, I have one more comment. Thank you so much for your speech. My question is, you have mentioned that it is possible to scale up the synthesis of scuderidites by ball milling. How many can be prepared?
We were preparing on what for us was a large scale. When we work on sealed tubes, for instance, we work on 3 to 5 grams. So when we went up to 60 grams, that was quite a big leap for us. We have looked at going further, and I think with kind of laboratory-sized ball mills, you can get up to maybe 80 to 100 grams. But I know that I've been in discussion with Peter Balash in the Czech Republic, I think he is. I always get confused, I'm afraid. And he's got sort of more industrial scale mills, and he's producing materials on the hundreds of grams scale by ball milling. So ball milling, if it works, it's a very scalable method.
Okay, so I'm not sure if there's any more questions. So if it's not the case, maybe we should move on to the next speaker.
So the next speaker is Dr. Elizabeth Castillo Martínez. She is a Spanish chemist who is currently working as an associate professor in the Department of Inorganic Chemistry at Complutense University of Madrid. Her research is focused on developing new materials for sodium and potassium-ion batteries and designing new chemistries for low-cost energy storage and conversion applications. She finished her PhD at Complutense University in 2008. As a postdoc, she got research contracts and postdoctoral grants in Dallas and Cambridge University, where she was awarded a Marie Sklodowska-Curie postdoctoral fellowship. Along her research career, she has participated in more than 20 research projects in different areas, leading a research on time temperature indicators and wearable batteries at Nanotech Institute in Dallas, sodium-ion projects in Think Energy Gune, a research on MOFs and COFs for energy storage at Cambridge, and her recent work in the search of anodes for potassium-ion batteries. Since then, she has co-directed 3 PhD students and 2 more going on, and has supervised several master's and undergraduate students, as well as participated in communication and outreach activities and in the organization of international meetings such as First Symposium in Sodium-Ion Batteries. As it is clear, she has always demonstrated creativity and excellent capacity to carry out original research wherever she was. So thank you, Elizabeth, for coming today. It is a pleasure having you.
Thank you very much for the kind introduction. And thank you, Jesús, and the organizers for inviting me to be part of the symposium. For me, a pleasure to be part of this, and thank you for a very nice talk. So what I'm going to be talking to you about today is about the next generation of batteries. And my idea is to give you a very general overview of all the different chemistries. I have to say before starting that the topic is very broad. The number of different chemistries that has been being developed is very, very vast, and I'm sure I will leave some unexplored areas. So, but I would like to give you like a general feeling of all the things that are going on, even if I will be talking very briefly about my own research. So let me just try to increase a little bit my volume. Yeah, and I'll just use the laser. Yeah, and I'll just start. So as a starting point, I would like to start by setting up what is a battery. You all know it's a device that converts chemical energy into electrical energy. And to show this, we can look at the example of the first battery that was invented by Volta more than 200 years ago. What happens is that an electrode from the anode, or electrons from the anode, travel through an external circuit to a cathode. In the case of Volta's battery, this where the cathode was copper, the anode were zinc disc, and they are separated by a fabric which is soaked in salty water. The salty water acts as a ionic conductor for charge balance. So what is going to determine how much energy can we store in a battery? What determines this is there are two factors. The first factor is the energy difference between the energy levels of the electron, the anode, and the energy levels that the electron is going to occupy on the cathode. This energy difference is called voltage difference and is one of the main aspects of a battery. So as you can imagine, batteries in which we have lithium, they have a very high, the electrons that are shared or that are released are in very high energy levels, and therefore batteries composed or batteries in which lithium metal is involved have very high voltage. The other parameter is the amount of electrons that you can release, since each electron that travels from the anode to the cathode will release this amount of energy. If we were to look at a voltage versus capacity plot, which is typically what we see when a battery is discharged, the total energy, that is energy density of this battery, would be the energy, the area under the core. So lithium is the lightest metal, and also I think it's the lightest solid at room temperature and pressure, and therefore, even if it releases only one electron, it can release lots of electrons per unit of weight. Also quite a lot of electrons per unit of volume. So I think with these two terms, voltage difference and number of electrons, you can agree that you can understand why actually lithium-based batteries are dominating the portable electronics market. Can you hear me well? Sorry, is it too low? Should I speak fast, louder? I don't think. Let me see if I can increase my. That's all I can do. Sorry. I will try to get closer to the microphone, or maybe I just need to move the microphone. Can you hear me better now? So this is the reason why lithium-ion batteries are all around us. And actually, that's the reason why you all have lithium-ion batteries in your cell phone and in your laptop. But the importance of this invention, actually on the invention of the lithium-ion batteries that power our electronic devices, was recognized actually with the Nobel Prize of Chemistry in 2019, which was awarded to Professor John Bannister Goodenough from the University of Texas at Dallas, Professor Stanley Whittingham from Binghamton University in the state of New York, and Dr. Akira Yoshino for their development of the lithium-ion battery that led to their commercialization by Sony in 1991. So if we were to look at how at a plot of energy density, volumetric energy density in watt-hours per liter versus gravimetric energy density in watt-hours per kilogram, it is clear that lithium metal-based batteries are in the top right corner. However, lithium metal-based batteries are unsafe so far, and that's why our batteries, our nowadays batteries, are mostly based on lithium ions, but do not contain lithium. If we see how the energy density of commercial 80 millimeter in diameter, 650 millimeter in height cells, these cylindrical cells, has evolved during their 30 years of their commercialization, we can see that both gravimetric and volumetric energy density has increased maybe by threefold. And this increase in battery performance is due to both changes in the chemistry of the batteries as well as chemistry changes in the engineering aspect. So if we were to look at one of these cylindrical batteries from inside, we will see that they are actually consist of a roll of many thin films stacked one on top of each. These thin films will be a cathode, a copper anode current collector, then the active material, the anode itself, which in the case of commercial lithium-ion batteries is graphite intercalated with lithium, then a polymeric separator, which has a microporous structure, and it's designed so that if the temperature rises because of some short circuit event, the pores close, and then the short circuit can be stopped. Then the layer of cathode material, which in the first commercial ion batteries, it was lithium cobalt oxide, and then the aluminum current collector on the cathode. As you can see, both the anode material and the cathode material have a layer structure, and they have capacities about 370 milliamp hour per gram and 140 milliamp hour per gram. You don't need to remember these numbers, of course, but this is to give you an idea, as I will be talking to you about other values for other materials that have been developed. And what is important is that the voltage difference at which the reaction, the redox reaction takes place on both the cathode and the anode is quite large, about 4 volts approximately. But the development of these batteries had other issues to be solved. So if you were to actually, these batteries, we said that they had an electrolyte in which ions move. And actually for lithium-ion batteries, this electrolyte is composed of lithium salt, lithium perchlorate, or lithium hexafluoroarsenate, or lithium hexafluorophosphate, the most common case, in a mixture of carbonate solvents, propylene carbonate or propylene ethylene. What you can see here is that this electrolyte is actually thermodynamically unstable in the presence at the very low voltage at which is injected into graphite, and therefore there is a continuous decomposition of electrolyte. The addition of ethylene carbonate to the electrolyte mixture, what makes is to promote the formation of a passivation layer on top of the material that allows the voltage to continue going down and the lithium ions to insert into graphite, and this becomes reversible. So it is the formation of this passivation layer has become a very important issue in batteries. It depends a lot on the chemistry of the electrolyte, and it depends a lot on the chemistry of the electrode material. And depending on this, you will have a layer which has like a kind of polymeric matrix with inclusions of inorganic salts. And depending on the thickness of this layer, you will have more or less resistance, because this layer must be electronically insulating, but it must be ionically conducting. So actually, the lithium ions can still go inside and outside of the electrode. So this is a very important and active area of research. Every time any new chemistry is developed, especially this high energy density alkali and alkaline earth chemistry. But as you can imagine, after the development of these commercial batteries, research didn't stop, but on the contrary, there was a lot of activity. And from the layer structured lithium cobalt oxide, there was a movement towards more sustainable cathode material. So instead of using cobalt, which is mined in Congo mostly and in not very humanitarian conditions, let's say, other materials composed of manganese or iron as the transition metal, which are much more abundant and sustainable, has been developed. The lithium manganese spinel was developed as well in Professor Goodenough laboratory at Oxford and with his postdoc Mike Thackeray. And this crystal structure has three-dimensional tunnels for lithium-ion diffusion. This higher dimensionality with respect to the layer oxides gives this material higher power and allows it to be used for applications where higher power is required. On the other hand, the even more friendly lithium iron phosphate, which was developed also by the group of Professor Goodenough, but this time at the University of Texas and Austin, it has an olivine type structure where only one-dimensional tunnels for lithium-ion diffusions are there. This imposes some more limitations on the material, both ionic and electronic conductivity, but this can be overcome by properly nanostructuring the particles so that the tunnels where the lithium ions has to diffuse are along the short direction in platelet-like particles, and also by carbon coating the nanoparticles. In fact, this material is very much wanted for some applications like electric vehicle, because it doesn't have some of the issues associated to possible oxygen release that can occur in oxides. Given the fact that in a polyanionic compound, such as phosphates, the covalent phosphorus oxygen bond holds the oxygen atoms much more strongly in the structure. And if there is overpotential in the cathode during the charge of the battery, the oxygen ions are still very well attached. However, we still want to go towards higher energy density cathodes and anodes, and actually research activity on this area has been very intense. Starting from the lithium cobalt oxide, replacing cobalt by nickel led to higher capacity, because in lithium cobalt oxide, only half of the lithium ions could be reversibly extracted. With nickel, you can achieve larger amount of extraction. However, they have a high reactivity towards the electrolyte and also high thermal reactivity. So strategies involving doping, such as cobalt that avoids lithium with nickel mixing that occurs in the pure composition, or doping with some electrochemically inactive elements such aluminum 3+, allows to have materials with high rate of. Actually, this composition is used in many commercial batteries, and you will hear of it as NCA. The other composition that has scoped the market as well is the NMC, or nickel, manganese, and cobalt, whereas manganese replaces aluminum, which is also another low-cost and thermally stable material. And actually, for this composition, the technology that has been developed and that is mostly used is a technology based on a gradient of composition of spherical secondary particles. So the material synthesized having a gradient of composition, so pure nickel phase, I mean doped with cobalt to avoid the anti-side disorder, is formed at the core of the particles, but there is a continuous gradient in composition as you go towards the outer surface, and the composition becomes manganese-rich to avoid reactivity with the electrolyte. And this gives a material with a capacity of about 250 milliamp hour per gram, which is quite high compared to the 140 of the lithium cobalt oxide. Another strategy that is being investigated is the use of lithium excess layer material. This material, and actually what I'm going to be talking about from this point, are materials which are not in commercial batteries yet. The 5 materials I talk about are the materials that make it batteries for the time being. But these materials have a lithium to transition metal ratio, which is larger than 1. This means that in one interlayer of between oxygen lattices, you have only lithium, but in the other layer, you have a mixture of lithium and manganese. Surprisingly enough, this gives capacities which are above the capacities of the NMC compositions, and also a very large plateau on the first chart above at about 4.6 volts versus. And there is a lot of discussion about this, and it seems that the most agreed argument is that the high capacity is likely due to an ion redox on the oxygen sublattice. But this is an issue because the oxygen can evolve. And although in the bulk of the particle, the oxygen is not released, it just reacts kind of reversibly. In the surface of the particle, there is some oxygen loss, I mean, an ion redox. And this leads to transition metal rearrangement. And because there is a transition metal rearrangement, the voltage of reaction. So what is observed in these materials is that the capacity, the discharge capacity, as well as the average discharge voltage goes down as we are cycling. So despite these materials have very high capacity, they still have some issues that keeps them far from. Other type of materials that has called lots of attention are those materials based on conversion reactions. They can insert also more than one lithium ion per transition metal, but in this case, all of the reactivity is due to the transition metal, to the redox properties of the transition. Here you can see a plot in which in 1980s already, the insertion of up to 4 lithium atoms in lithium iron oxide, in the layer lithium iron oxide, takes place. And if we look at the chemical formula, we can actually see that here the iron oxidation state is 0. And what happens is that we actually have iron 0 and lithium oxide. So although this type of reaction was known from the 80s, and it was reported for many oxides, nitrides, and sulfides, it was not until 2001, sorry, my slide is until 2001 that high cyclability was reported at room temperature for nanosite, cobalt oxide, and both the rock salt and the spin crystalline structure. And what is found in the room temperature cyclability is that actually the first discharge plateau is quite different from the following cycles. And this is because actually the structure that is cycled in the first cycle is different from that of the following cycle. Indeed, during the first discharge, what is proposed to be formed is that metal nanoparticles are formed within a matrix of the oxide or nitride or sulfide of lithium. And with also some phases from the electrolyte decomposition. Moreover, what is seen is that there is some additional capacity to that expected for the insertion of 1 or 2 or 3 lithium ions. And this has been assigned to some interfacial storage on the surface of the metallic nanoparticles, as well as to some possible further reactivity of the decomposition products of them. So although using these materials with huge gravimetric capacities would be very desirable, the large hysteresis and large first cycle Coulombic inefficiencies prevent them from going to market. Still, the mechanisms of reaction are still being explored. And indeed, for example, for the iron difluoride, rutile iron difluoride, it's been recently discovered that actually the reaction taking place is not just a pure conversion reaction where all the iron fluorine bonds are broken and new lithium fluoride bonds form, but by a study from PDF. Let's see if I can play the video. No? Well, there is a video here. Yeah. Well, that shows by using a non-matrix factorization algorithm, a new phase appears, and this phase can be modeled very well as a lithium 2 iron tetrafluoride. And actually, this phase is thought to be an interfacial structure which is formed to accommodate the very large structural rearrangement between the iron difluoride and the lithium fluoride. But actually, this phase can be coherently linked to both initial and final phases and seems to buffer the large lattice expansion and contractions between phases. So instead of explaining this reactivity with a one-step conversion reaction, we could explain this reaction as a two-step displacement reaction where lithium ions displace iron from the sublattice, and then the insertion of further lithium ions again completely extrude the total amount of iron. On the anode side, there has been lots of reports as well on trying to use high-capacity anodes. Remember that graphite has about 370 milliamp hours per gram based on the insertion of 1 lithium ion per 6 carbon atoms. But when lithium reacts with group P elements like silicon, aluminum, tin, germanium, lead, it can react through alloying reactions, which can give much higher capacities. For example, in the case of lithium, it can form lithium Si4, which has a capacity which is 10 times that of graphite. However, as you can imagine, if almost 4 lithium atoms per silicon atom enter into the structure, there is a large volume expansion with cracking of the particles, and after many cycles, these particles get completely pulverized. Not only this happens to each individual particle, but also the SEI layer that forms on top of the particles during the decomposition of the electrolyte in the first discharge also get broken. And in the subsequent cycles, new SEI layer needs to form on the surface of the new particle. Therefore, a very thick SEI layer that then prevents a proper lithium-ion diffusion gets to be formed. Many strategies have been developed to try to overcome this, like compositing nanoparticles instead of micron size with carbon materials, putting silicon nanoparticles in a silicon oxide matrix that can buffer the volume expansion, as well as using different types of binders, which could be electronically conducting, and branch polymers, which can have a better addition to the silicon particle. Indeed, silicon is being used for some demonstration. I think it's not yet in the market, but many battery manufacturers are introducing, if not 100% silicon, a certain amount of silicon in their anode formulation. But still, the ultimate anode will be lithium metal. I mean, of course, we will have higher capacity with lithium metal than with silicon. And higher energy density batteries based on lithium metal instead of the rocking chair principle, where the lithium ion moves from one electrode to the other, could be a way to have higher energy density. However, let's remember that, I don't know if I told you at the beginning, but lithium metal was indeed in the first rechargeable lithium-ion batteries. Actually, Professor Bittingham, who proposed the lithium titanium disulfide battery in the 1970s while he was working at ExxonMobil, they commercialized their batteries with the lithium aluminum alloy anode, as well as Moly Energy commercialized as well lithium molybdenum disulfide batteries. And they had to withdraw their batteries from the market very fast because there were always problems of source circuit. And this is because of the dendritic growth of the lithium ion. I'm going to show you another video if I can, in which we can see, I hope you can see, we can see how lithium, when the battery is discharged and lithium is supposed to be plated on the lithium electrode. I can't show you the video. I wanted to show you a video where you can see, but you can find it in this reference if you are interested, where you can see that sorry. Yeah, I'll move on. Yeah, so what lithium does, instead of forming a homogeneous thin film, it does grow in a very unhomogeneous way, forming like dendrites. And these dendrites tend to grow towards the opposite electrode, and sometimes they cross the separator and reach an short-circuiting event. Oh, here it is. You can see the unhomogeneous growth, okay, while we are going down in voltage just towards lithium volt, 0 volts. So if we want to make batteries for electric vehicles, which is one of nowadays concerns, I think nowadays we need to make better batteries for electric vehicles and better batteries for large-scale stationary applications. So if we want to make batteries for electric vehicle, we need to get rid of the flammable electrolyte that we have in our current battery. Lithium PF6 in ethylene carbonate, propylene carbonate, when the battery is short-circuited, it heats up and it can lead to explosion. So we want to get rid of the flammable electrolyte, which also in contact with air can form HF, and also if heated up can form some organofluoro compounds, which are not very nice for our health. So what can we do? We can use, instead of a flammable electrolyte, we can use solid electrolytes. And here there has been different strategies. One of them has been the use of a polymeric electrolyte, which actually was proposed by Professor Michel Allemand already in 1987, where he proposed a rocking chair battery made of the cathode and a graphite anode. And to make the contact between the cathode and the polymer electrolyte with less interfacial resistance and to help the lithium-ion charge transfer, typically the polymer electrolyte and the cathode are mixed on the cathode side. There is, of course, then a layer of polymer electrolyte free from the cathode. And the good thing of this polymer electrolyte is that there is no decomposition, so no SEA layer formation. Actually, these polymeric batteries, together with the lithium iron phosphate, has gone into commercial batteries, and it is using the blue car that's running in Paris since 2011, as well as in the blue bus that is running in Paris as well, 2005. Other strategies is to use ceramic electrolytes instead of polymers. We know that ceramics can also be a good ionic conductors. And indeed, the first sodium sulfur commercial battery made by the Ford Motor Company in 1967 contained a ceramic beta alumina electrolyte, which transferred the sodium ions from a molten sodium tank to a molten sulfur tank. And this was at temperatures of 300 amps. Actually, it was in order to study the conductivity, the ionic conductivity of this beta alumina, that then Professor Bittingen took some insertion electrodes, which could have variable amounts of sodium into their cavities, and to do this measure, and somehow made this insertion chemistry, or started this insertion chemistry. Actually, beta alumina was also used at room temperature by Professor Michel Allemand on a sodium battery with a graphite intercalation. And since these late 70s, actually, since this works from the not so late 70s, many lithium-ion ceramic conductors, and mostly focus on lithium once the lithium-ion battery is off, has been proposed, and these are based on the lithium superionic conductor structure, the perovskite lanthanum lithium titanate, as well as the garnets or the amorphous lipon gases and sulfides. If we were to look at a plot of ionic conductivity, well, this is the logarithm of the ionic conductivity versus the inverse of temperature, we can see that the liquid organic electrolyte has conductivities at room temperature, which are in the order of 10 to the minus 2 Siemens per meter. And actually, some of the sulfides that has been proposed to have similar conductivities as well. However, what is more striking, and this is quite recent, is that there are some lithium-rich or sodium-rich glass electrolytes as well, which are derived from the antiperovskite structure, that show conductivities which are very comparable to those of the liquid electrolyte as well, and even higher than that of the sulfide. And in some sense, these materials are not as sensitive as sulfides, although they have to be treated with some care as well. This type of glass electrolyte additionally have a very large voltage stability windows of excess of 8 volts. You can see they don't decompose at 8 volts above lithium ion. And what is very important, they have very good wetting properties towards lithium ion, and they enable the reversible plating and stripping of lithium metal. Actually, they can be plated and stripped for more than 24,000 cycles in a lithium glass cell. And very interesting features are being shown by this glass electrolyte, which seems to be contributing also to the capacity of the materials. So when making batteries with a lithium metal and a cathode material, not only the capacity from the cathode and lithium materials are achieved, but it seems that there is an additional contribution coming from the electrochemical double layer capacitors that are formed on the surface of the electrode. And this is seen as an increase of the specific capacity with the number of cycles, which is actually very unusual and not really seen in most of usual lithium-ion battery material. I mean, at least in conventional insertion, intercalation, or conversion. So if we could use lithium metal with some of these polymeric, ceramic, or glassy electrolyte, what would be the best cathode material? And although we've seen many inorganic oxides, which will be great oxides and polysulfides, polyphosphates, polyanionic compounds, sorry, phosphates and sulfides with as electrode, actually, in terms of capacity, we could even beat them with sulfur, elemental sulfur, and elemental oxygen. And that's what actually has been made. Their specific capacities for the formation of lithium sulfide and lithium peroxide are very large, more than 1,500 milliamp hour per gram. This is almost 10 times that of the largest capacity cathode material. But of course, these batteries also have some problems. For example, if we look at the lithium sulfur batteries, sulfur is very insulating, so you need to add a lot of conducting carbon. But also, once it starts being reduced, it starts forming polysulfides, which in the case of liquid electrolytes, dissolve this polysulfide. If these polysulfides are dissolved, they can travel through the electrolyte towards the lithium metal. You have a redox shuttle events, which result in low Coulombic efficiencies. I mean, the battery is getting self-discharged. And indeed, if you look at how the battery is discharged after 30 minutes of being charged, or after 1 week of being charged, you will see that the capacity, which is delivered, gets much lower because these batteries have issues with self-discharge. Of course, there is an intense research on lithium sulfur activities to alleviate issues, like putting protective layers, making composite, having the sulfur trap into some carbon nanostructures to avoid these polysulfide redox shuttle events. On the other hand, the lithium air batteries, which were first shown in 1996 by Professor Abraham, do have even higher redox voltage, I mean, very close to 3 volts, and similarly high theoretical capacities based on the weight of it. However, if we think that we are taking the oxygen from the atmosphere, we somehow have some infinite theoretical capacity. But actually, lithium in contact with oxygen is forming most of the times lithium peroxide, and this lithium peroxide is a solid that once in the battery, does contribute to the weight and to the volume of the battery. So the capacity is actually not infinite. If we were to compare the theoretical and practical specific energy and watt-hours per kilogram of different battery chemistries, we see that the lithium air is by far the one that shows the largest capacity. But also, if we reduce the contribution from all the external components like casing, carbon collectors, the practical capacity is not that much. Nonetheless, the theoretical capacity approaches that of gasoline, And that's why lithium-air batteries are on the spotlight for making it into electric vehicles. Some issues related to this chemistry is that in the presence of liquid electrolyte, the previous example was with polymeric electrolyte. In the case of liquid electrolyte, there is electrolyte decomposition, and this reaction, of course, is not reversible. And also that the lithium peroxide is clogging the pores, and then when you want to discharge the battery, you want to bring the lithium peroxide back into oxygen, you have an issue because the electrons are coming from the carbon. And you start by reducing the lithium peroxide in contact with the carbon. So once this is all, oxidized, once this is all oxidized, the remaining lithium peroxide gets disconnected from the carbon, and therefore you have lots of dead weight, which is not reversible. So in this sense, what the main strategy has been to use redox mediators, which are soluble in the electrolyte, and actually instead of reacting with the lithium peroxide particles in the region where they are in contact with the electrode, they do react with the bulk of the lithium peroxide in solution. And this proves to be a very big improvement in reversibly reacting this battery chemistry. So it is important that the redox mediator is soluble in the electrolyte, that it has an oxidation potential above the oxidation potential of the lithium peroxide that we want to oxidize, and of course that this reaction is very fast enough. A breakthrough in lithium-air batteries came in 2015 in the group of Professor Gray, when they used highly porous reduced graphene oxide electrodes, as well with a lithium iodide redox mediator and some unwanted amount of water, well, unwanted at the beginning, but then wanted and controlled, in which actually instead of forming lithium peroxide, it formed lithium hydroxide. If we form lithium hydroxide, we are getting 4 electrons per oxygen molecule instead of 2 electrons, and the capacity can be increased further. And the presence of the lithium iodide redox mediator helps on decomposing as well the lithium hydroxide product as would be for the lithium peroxide. Interestingly, water is needed to form lithium hydroxide, but the lithium iodide is also needed to form lithium hydroxide, because lithium hydroxide catalyzes the decomposition products of the peroxide species. And in the absence of lithium peroxide, lithium iodide, it is lithium peroxide that forms. However, if there is lots of water, the water cluster traps the lithium iodide, and then it decreases its catalytic activity. So there is an optimum range in which an optimum water content that can be put into the electrolyte to have the desired lithium hydroxide reactivity with proper reversibility. This can be further seen in these photographs where different amounts of water were added to a solution of hydrogen peroxide, and some lithium iodide and DME were added. And when the amount of water was adequate, there was oxidation from the iodide to the triiodide, and therefore the solutions were colored. Still, even if this chemistry seems very promising, there are still some issues to solve. For example, this battery actually works with oxygen, not with air, and it is necessary to take also into account that you need to avoid CO2, you need to avoid some other atmospheric pollutants, as well as to avoid this redox mediator to travel from the cathode to the lithium metal. If we were to compare the lithium-air batteries with other metal-air batteries, we see that in principle, the specific energy for a lithium-air battery based only on the weight of lithium and oxygen is much higher than for any other chemical. But if we calculate the specific energy based on the weight of the decomposition products, this lithium peroxide or sodium peroxide, then differences are not that large. And especially if we take into account that aluminum, magnesium, although they are thermodynamically unstable in water, they can form some passivation layer that allows them to operate. Actually, zinc-air batteries are amongst the most studied metal-air batteries and among the most developed batteries. And one of the most important challenges are to control the kinetics of the oxygen reduction reaction and the oxygen evolution reaction. So control over the catalyst and about the along the cathode architecture needs to be considered. So this will be what concerns car electric vehicle. What about large-scale storage? Of course, the requirements for large-scale storage are very different than those for electric vehicle. And here, the more important criteria is the sustainability. So even though lithium is relatively abundant, we can find, although it's kind of geographically located in some specific areas, like in South America or in Afghanistan. But I think every day there are more and more mining places. Actually, we have some mining place in Spain as well. But still, you can see that aluminium, calcium, sodium, magnesium, or potassium, any of these elements are at least 1,000 times more abundant than lithium. So I think if we want to make massive batteries for electrochemical energy storage connected to renewables, we need to go to these other chemistries: sodium, potassium, magnesium, calcium, or aluminum. It is not only this element that needs to be considered. Of course, we also need to consider the methods of synthesis of the electrode materials and their recyclability and their processing. But one of the concerns is, of course, the use of lithium, as well as the use of cobalt, which I think it could be completely forgotten for stationary applications. So sodium and potassium ion, which are monovalent as well as the ion, do share in principle most of the same principles of operation of rechargeable lithium ion. And indeed, many of the processing parameters, like particle processing, how to make secondary particles, the composition of the laminates, that where besides the active material you have a conducting carbon and you have a binder, the additives that are used in the electrolyte for the formation of the solid electrolyte interface, many of these parameters can be transferred from the lithium and sodium ion battery to the, from the lithium ion battery to the sodium and potassium ion battery. However, actually, each of these chemistries has its specific issues. I mean, they are different. The abundance we've seen is 1,000 times more than lithium, but also the ionic radii change and its reactivity as well. One of the most important things is that, for example, sodium does not intercalate into graphite, which has been until now the most popular anode material for commercial lithium-ion batteries. You can see in this plot the discharge and charge in the insertion and the insertion of lithium ions into graphite. And here, in very small in dashed line, you can see the insertion and the insertion of sodium ions has almost no capacity. And actually, this makes sense because the voltage for sodium plating is about 0.3 volts above that of lithium. And therefore, sodium will plate before lithium could be intercalated. However, it is possible to intercalate sodium ions with co-intercalated with some solvent molecules at higher voltages, but as well at a lower capacity. But interestingly, this co-intercalation does occur at a relatively fast rate. The fact that graphite doesn't intercalate sodium ions has motivated lots of research to search for alternative anode materials. And I'm going to show you an example of my own research here, where we prepare polymeric bases and propose them as electrode materials. And actually, we saw that the redox processes, two redox processes, which change in voltage with the change of substituents, of course, do take place at voltages close to 1 versus sodium plating. And therefore, it's interesting for anode material for sodium ion batteries. We could also go to lower voltages if we hybridize these SIF-based units with carboxylates, or we could even make self-binding thin film by copolymerizing the SIF-based functionality with polyethylene oxide unit. These materials actually have relatively good performance, although if we look at this plot of specific energy, considering the weight of the anode and cathode material, for a positive electrode composed of a layered sodium oxide by the British company Faradion, give us the different, taking into account the specific capacity of each anode material and the voltage at which the reaction takes place, which is indicated by these dashed lines, we can see which is the specific energy of the system. And we can see that actually sodium-ion batteries do have a slightly lower energy and specific energy than lithium-ion batteries, but they have other advantages, such as you can use an aluminum current collector in both electrodes instead of having to use the copper current collector that is in the lithium anode, because sodium as well as potassium do not form alloys with aluminum, and therefore you don't need to use copper. And aluminum is lighter than copper. Tin-based anodes and phosphorus-based anodes do have very large capacities because they are mostly based on the alloying reaction, and therefore they do have the issues related to pulverization and large volume expansion of alloys material. And hard carbons are actually the alternative that is being used in the initial commercial sodium-ion battery. On the other hand, if we look at the cathodes, we can see here in yellow the volumetric and energy density and capacity of lithium layer oxides, as well as many different sodium cathode materials. We can see that for layer oxides, we have many more compositions than for lithium ion, and this is due to the fact that you can de-intercalate sodium ions from layer oxides of many more transition metals, not only cobalt and nickel. Also, polyanionic compounds, phosphates and fluorophosphates have been tested, as well as some hexacyanometallate or Prussian blue-based materials, which on the other hand have lower volumetric energy densities, therefore do not appear in this plot. But it is the layer oxide that have the highest volumetric energy density, and the hard carbons has the highest energy. If we move from sodium to potassium, we can see that potassium ion does plate at voltages which are even below lithium plating, and therefore, in principle, one could even achieve voltages higher than those of lithium batteries. However, of course, there is a penalty on the weight of the potassium ion for the gravimetric energy density, and most of all, the main concern is that actually potassium metal is quite reactive, and we want to avoid potassium plating. And therefore, even though the voltage is lower, we will look for anode materials which are not very low in voltage or very close to potassium. Nonetheless, many people are looking into safely plating potassium, as this appears as a possible high energy density battery. For potassium-ion batteries, the Prussian blue materials are the preferred cathodes because their tunnel size perfectly matches the size of the solvated potassium ions. And you can see that the voltage is quite higher than that. The voltage of insertion of potassium ions is higher than the voltage of insertion of sodium ions in the same structure type. For the anode, graphite do show a 60% volumetric expansion when potassium is intercalated into graphite. It's quite large, and therefore it is also interesting, and this is one of my current research areas, to look for alternative anode materials for potassium-ion batteries. Nonetheless, it can be seen that by changing the binder from typical PVDF to polyacrylonitrile, the first cycle Coulombic efficiency can be reasonable. I mean, 80% is a reasonable value for a first cycle, and the capacity can keep some stability. So when investigating new anode materials, it's quite important to run in parallel the research of the electrolyte and the binder combination. So sorry. So what is beyond lithium, beyond sodium and potassium ion? We have the multivalent chemistries. We've seen already they are all very abundant, and magnesium and calcium, specifically calcium, has a voltage of reaction which are very close to those of sodium and potassium. However, both of these chemistries, I mean, magnesium intercalation was investigated earlier, but calcium ion batteries has started to be explored more recently, and they do not have larger specific capacities, but actually because they can exchange 2 electrons or 3 in the case of aluminum, the volumetric energy densities are even higher than that of lithium-ion batteries. An additional advantage is that when these metals are plated, dendrites are not formed. The main difficulty, however, is to find a good electrolyte that allows the plating, because we have cations with very large charge densities. I mean, we have a charge of +2. They tend to form ion pairs with their anions in the electrode, and also they tend to get very large solvations there. So it is quite complicated for the charge transfer to take place. So the strategies that are being used are to use high temperature, use large delocalized cations, as well as the use of ether-based solvents rather than carbonate solvents. Another issue with these multivalent chemistries is that it's difficult for the cation also to be inserted and extracted from a cathode host. Indeed, softer anions, such as sulfides, are preferred for the cathode material rather than oxides. And for magnesium batteries, it's the Chevreul phase, the molybdenum sulfide phase, which has shown the best performance, although the magnesium diffusion barriers are not very large in some sulfides and selenites as well. But for calcium, the best performance achieved so far is with titanium disulfide, and this takes place at very high temperatures and still relatively low C rates. So there is a lot of progress still to be made for these technologies to reach actually the market. The final multivalent chemistry will be that of aluminum batteries. Aluminum exchanges 3 electrons when it is electrodeposited or already solved, but it will have even more problems than calcium gas or magnesium gas to be intercalated into graphite. So the strategy to use electrolytes in which the aluminum ion gets coordinated by chloride anions, and actually what is intercalated is a single charge anion, the aluminum tetrachloride, that can be intercalated and intercalated relatively. So it is possible to achieve reversible cycling during 200 cycles and even more during thousands of cycles of this aluminum graphite battery. And to end, I would like to talk about another type of battery, which is quite different from all the batteries I've been talking about, and these are redox flow batteries. Very different from the previous chemistries is that instead of having solid electrodes where the ions get in and out and the electrons get in and out, we have the redox active species are dissolved in a solvent, so they are stored into tanks, and they go through the current collector to suffer the redox reaction. So redox flow batteries can uncouple energy and power because the energy density is determined by the size of your tank, whereas the power is determined by the size of your electrode. And the current chemistries in lithium in redox flow batteries are vanadium, which is the most popular, in which you have vanadium 2, vanadium 3 redox couple in the anolyte, and vanadium 4, vanadium 5 in the catholyte. Having the same chemical species is an advantage because you have a kind of symmetric battery where cross-contamination doesn't get such a big impact. Still, these aqueous suspensions have quite a low pH as they are in concentrated sulfuric acid. The other chemistry that dominates redox flow batteries is that of zinc bromide that reaches very large solubilities up to 8 mol. Of course, the larger the solubility, the larger the energy density of the chemistry. So increased solubility is one of the most important aspects in redox flow batteries. And then having a large voltage difference between the reactions that occur in both elements. But all these chemistries have corrosion, cost, and toxicity uses. So if we are going to make very large batteries for large-scale stationary applications, we want to move to more sustainable chemistries. And in 2014, actually, an example using anthraquinones, which are organic materials, very sustainable, made from biomass, where you can tune the redox voltage by changing the groups, was proposed. After this work, actually, in the last few years, many different anolytes and catholites have been proposed, both in acidic, basic pH, as well as neutral pH. And it's opening quite a broad range of possibilities for the development of very large redox flow battery installation. Myself, I was involved in developing symmetric redox flow aqueous batteries, in which we were using dyes, which we functionalized to get a species that could be both oxidized and reduced, and therefore would enable to be used again in a symmetric battery, with all the advantages that I've already discussed in terms of minimizing the issues with cross-contamination through the membrane. Still, although these materials seem to perform quite well and we reach solubilities of up to 2 mol for some cases, there are still some issues related to how the solubility changes when you go to the reduce or to the oxidize or to the reduce. And this symmetric battery is just one of the redox flow battery configurations. The most common for the vanadium flow is with an ion exchange membrane. And in the fact that we have a symmetric battery, we could use a porous separator instead of an expensive ion exchange membrane. Also, if we have polymeric electrolytes, we can also have a size separator, which will bring down the cost of the battery. And I think one of the ultimate configurations will be a membraneless redox flow battery, where the two electrolytes do not mix because of immiscibility. And therefore, you avoid also some of the issues related to cross resistance, to large resistance between the membrane. So, in summary, I think I hope I've given you an overview on the current status of lithium-ion batteries, what the next generation of lithium-ion batteries could be with high energy density materials and solid-state lithium metal batteries, specifically for electric vehicle application, and what will be the next generation of more sustainable lithium-free batteries, which will depend on high energy density, sodium, magnesium, or calcium metal batteries, or even closer to the market, I will see sodium ion or potassium ion batteries, as well as redox flow batteries. It has been in the market for some years, especially the vanadium redox flow battery. But we would like vanadium-free redox flow batteries to be developed. So I'd like to just say that, as I hope you have the idea that each chemistry has its own issues and there is not a perfect battery chemistry. And I would like to thank you all for your attention. And I would like just also some of my colleagues were part of the little things I show you from my research. If you have any questions, I'll be happy to answer. I hope I didn't get too long, a bit. I can't hear anything.
Yes, thank you so much for participating in this workshop, Dr. Elizabeth, and for this interesting talk. It's a pleasure to hear you talk about batteries, And if you don't mind, next move on to the questions. And to give time to the viewers, maybe I can start. So, how is the cost effective in potassium ion batteries related to the potassium extraction? I mean, is the production of this type of batteries really profitable?
So, I mean, in this sense, of course, sodium-ion batteries are more cost profitable than potassium-ion batteries, because even if they have relatively similar abundance, you can extract very large amount of sodium from the sea. So in this sense, I think sodium-ion batteries are still beaten. But still, potassium extraction is relatively simple, more than lithium extraction.
Okay. There is more comment. For example, there is a question from David regarding to versatility of sodium and promising potassium. How close are they to a former industrial application? Will they ever surpass the lithium ion?
Well, I think it's clear they will not surpass lithium ion in the sense of energy density. But as I said, I think the motivation for working with sodium or potassium ion battery is not reaching higher energy densities than lithium ion battery, but it's having a more sustainable system. And maybe we can keep the lithium for the high energy density batteries that we use for other applications. But I think the motivation is to have them for very large scale. Having said that, sodium-ion batteries do have already some commercial products. I think Faraday was one of the first companies already. I think it was already in 2015 when they brought their first battery to the market. I think I've lost connection for a bit. But potassium-ion batteries are still a little bit farther away. You also have to consider that research on sodium-ion batteries became very general about 2010, although potassium-ion batteries were initially investigated when lithium-ion batteries, sodium-ion batteries were initially investigated when lithium-ion batteries in the 70s and 80s, but they were not, they didn't become the general research topics such as they are nowadays until 2010, when the interest grew up. But for potassium-ion batteries, I think it is now 3 or 4 years that is becoming quite popular topic. So they are still a little bit farther away.
Okay, thank you so much. Another question from Elena. You talk about sheath bases as organic materials for anode applications, but wait, there is not the complete question here. So maybe I can read another one. Sorry, Elizabeth. Do they show lower stability than traditional inorganic materials, or would they be like to be used in large scale applications related to the?
Yeah, this is interesting. I mean, of course, sheath bases are prone to hydrolysis in contact with water, but this reactivity is not, they are not, at least the polymeric materials and the salts we have prepared, they don't show an extreme reactivity. And them outside, and you can keep them vial. You don't need to have them in the glove box. But I have to say, we have not actually measured very long-term cyclability, if this is what the question refers, if it refers to their stability in the electrolyte. It seems stable, they seem stable, but we have not measured like thousands of cycles, only kind of focus on showing what are their initial electrochemical properties.
Thank you so much, Elizabeth. Another question from Cynthia Redondo. For measurements in a laboratory, do you consider that alkaline metals as reference electrodes are reliable, or can there be other alternatives?
Well, this is actually one of the issues with highly reactive alkali metals. Yeah, they do, as you go down from lithium, sodium to potassium, reactivity increases, and actually lithium metal is quite good reference electrode, but sodium metal does show not to be a very good reference electrode. So it is always better to, you can use the lithium metal as a counter electrode and as a source of sodium. Sorry, the sodium metal as a counter electrode and as a source of sodium. But it is better if you can, of course, use another electrode which has, for example, a flat voltage plateau, and get this material in the middle of this plateau to act as an electrode material. However, this electrode material, is a very good electronic conductor who has a good reference electrode. So it's not that easy. So what typically you can do is just to do the measurements in a 2-electrode configuration using the sodium or potassium metal as your counter and reference, and then do other measurements. Do if you want to have more precise control of the voltage, do measurements in a 3-electrode configuration where you use different sodium or potassium metal as current collector, where you build up a very large PCI layer because there is a lot of electrolyte composition, and then pressure sodium or potassium metal as a reference electrode. But still, this is going to have some contribution from the electrolyte decomposition surface. So the preferred choice will be to use, as I mentioned at the beginning, metal electrode material in the middle of a plateau reaction, or just to use an external reference, like maybe a silver or a platinum wire, but careful with platinum to promote the composition of the electrolyte, but maybe a silver wire and some ferrocene to do it. But this is not very commonly done. I would think once you characterize your material in a 3-electrode cell, it is more common to then try to build a cell completely free of sodium or potassium, a 2-electrode cell against another cathode. If you're studying another material, against another cathode already well established.
Okay, thank you so much. And I think that we don't have much time for more questions. So thank you so much for participating, Elizabeth.
Thank you, Marta, for your questions. Thank you, everyone, for your attention.
En 3, 2.
Dear Anthony and dear Elizabeth, many thanks for the outstanding presentation you made today. I think it was really motivating to hear about the progress in thermoelectricity and batteries. So thank you for participating. And thank you all for coming. We hope to see you tomorrow in the second session of the workshop, where we will enjoy Professor Alario and Dr. Molero talks about superconductivity and reversible solid oxide fuel cells. So see you tomorrow.